fractional exponents, we could just reciprocate. That's it. Okay. Our new exponent here is going to be?
-1.
And what's the reciprocal of -1?
-1.
Not a trick question. Yeah, -1, x to the -1, and then plus c. And I think we would be okay with that. So a little exponent work to the rescue there. Okay. All right. Number 9. This one gets its own because it is just that important. That one. Okay. And I want to go through this without just referring directly from the table, because you can see what the answer is on the table. It's there. It's that special. But I want us to explain why it's that special just based on what we've just encountered here. Let's imagine that we rewrote this as a power. It would be x to the -1. I think we're all okay with that. If you were to add 1, what would the new exponent be? 0. What's the reciprocal of 0? What's the reciprocal of 0? Undefined, yeah, okay. So basically what we were saying is the antiderivative of this is undefined times x to the 0, all right? Which is clearly incorrect. But it does have an antiderivative, okay? A very special one, okay? An extremely special one. So this is the special case. And it is so special that it actually has its own line on your table of antiderivatives that should never be forgotten about and should always be there. The antiderivative is equal to the natural log absolute value of x plus c. Now, I have a question. What do we know about the natural log? Specifically, its domain. What do we know about the domain of the natural log? Say that again. Greater than 0, okay? This original function here, f of x equals 1 over x, does not have a domain of x greater than 0. It has a domain that just x can't be 0. So x could be positive or it could be negative. Would you agree? That we could plug positive 5 into here, but we could also plug in negative 2. Would you agree with that?
Yeah.
But if we anti-differentiated that, in order for us to include the positive x values and the negative x values, well, we can't take the natural log of a negative. Okay, we can't do that. So to fix it, we have to include this absolute value. Because if we plugged in, say, -5, well, if you plug -5 in, well, the absolute value of -5 is 5. So you don't have to worry about the negatives. Okay? So that absolute value takes care of the domain of the natural log while still allowing the function to exist as it normally would. Questions? Cool. Yes.
Is there like a special name for this or not?
No, just that. Yes. And really the red flag is this, is that if you add 1, you get 1 over 0x to the 0. Like, hopefully that is like, yeah, you know, like, I don't have red out here, but if I did, you know, error kind of thing, right? So, domain error, or think error, or something. Okay. All right. Okay, number 10. Let's talk about this one. X plus 2 times 2x minus 1. Okay. So, the thing that we are going to learn about integration and antiderivatives is that they are not as nice as derivatives. There is no function in existence that we cannot differentiate with some differentiation rule. If there's a function, we can differentiate any one of them. Okay? You find one, there's a derivative for it. The reverse of that is not true. Not every function has an antiderivative. At least not one that is of elementary functions. We've actually had to invent functions to be the antiderivative of some functions because they occur in applications. All right? And we'll talk about those later on in semester 2. Really in June, we'll talk about those types of things. But for right now, we have very simple rules. And that's nice. But the challenge with having simple rules is that we actually have to make sure that we're using the simple rules. And the one rule is this, is that you cannot anti-differentiate products. You cannot, okay? So having this times this, you cannot deal with. And you will actually not learn how to deal with this until June. Okay? As that sits right there. There is no product rule for antiderivatives that is very simple. There is for derivatives, not for antiderivatives. Okay? It's going to be gross. It's going to be not fun. But it will be fun in June. So what do we do with that? Well, we do have a rule for sums and differences. That's the one that we wrote down yesterday, that if f of x is equal to g of x plus or minus h of x, then capital F of x will equal capital G of x plus or minus capital H of x plus c. Okay? We are able to anti-differentiate sums and differences, but we are not able to anti-differentiate products. So, how do we make that product a sum and difference? We've got to expand. All right, so we would multiply. X times 2x, of course, is 2x squared. This is going to be negative x plus 4x. That'll be plus 3x minus 2. So just, multiplying those binomials out. Of course, negative x plus 4x, that's where the 3x comes from. Okay. So from here, we have 1, 2, 3 terms. So we can anti-differentiate. Here we go. The antiderivative of f of x is capital F of x. 2x squared. Well, this is just going to be 2 times the antiderivative of x squared. Well, the new exponent will be 3. So this will be 1/3 x cubed. How'd we do? Good? Plus 3 times the antiderivative of x. Well, the new exponent will be, well, what's the exponent now? 1. The new exponent will be 2. So this will be a half x squared minus the antiderivative of 2x plus c. And then we just simplify this, clean it up. Whoops. Notation, capital F of x. Okay. So this will be 2/3 x cubed plus 3 over 2 x squared minus 2x plus c. Yes. Questions? Questions? Okay. All right. So like I said, our goal today is just to introduce you to some notation and really kind of delve into this. So there are 3 kind of not small ideas, but 3 ideas that we want to talk about over the next 2 days. The first one is what I'm going to call the initial value problem. Okay. So, if we are given additional information about a function, or its derivatives, we can determine the value of the constant c. So the idea of an initial value problem is that we still don't want to compute these antiderivatives, of course. But if we're given additional information about the function, we can actually use that additional information to find the value of the c. All right? Because right now it's arbitrary, unknown. But now we can narrow it down to get a little bit more specific. So, for example, let's determine the function f of x for the oh. Okay. The first one, gonna be very nice here. F of x is equal to 2x minus 3. Or pardon me, f prime of x, sorry. F prime of x is equal to 2x minus 3. And we're gonna say that f at 0